So the purpose of this lab is to demonstrate a closed-loop control system using pulse width modulation. The difference between this lab and the previous lab is that with pulse width modulation, everything is done digitally on the output side. So if you notice, we have a power MOSFET here that's being fed by a bipolar junction transistor that interfaces the P-channel MOSFET with the rest of the USB or the HCS12 circuit here. We also have the same light bulb set up with a small temperature sensor going into the analog input. So the temperature in Celsius will be blinked on the 7-segmented LED like we did in a previous lab, so that code remains the same. Notice that we also have this 12-volt jumper that's needed for the power MOSFET. Take a look at the lab handout for the schematic so you understand how this thing is totally wired. In addition to what we did last time with an analog output, I've added one more little difference in this lab, in that the least significant bit here on one of these dip switches is going to be used for the program to either be in closed loop control mode where it's trying to reach a set point, or if you flip that switch, it's going to go into open loop mode, which allows you to use this potentiometer right here to vary the duty cycle to the lamp. Okay, so your program has to take a look at that least significant bit and decide which one it needs to do continuously. Now we have the same setup here with a laptop that does not have a serial output, so we're using a USB dongle. Now in your code you still need to have the offset gain and set point set as constants. Take a look at the lab handout for that. These constant values are going to be different than what we did previously because of the control system differences. The set point I've put here arbitrarily at 32 degrees Celsius to make it different than what we had before. So let's go ahead and execute this code in codewarrior. And as you can see, there's nothing happening quite yet. So let's go ahead and press the go button. And as you can see, the light bulb is on pretty hard. Okay, and the temperature is rising, 26, 28. It's trying to reach that 32 degree threshold. And so as it ramps up, notice that the intensity will begin to back off because the duty cycle is being changed by the code, the control system that you need to write. So we're almost at 32. In fact, we're only about a degree away from that. So we've reached 32, and you notice the intensity is way down. And pretty soon the light bulb may blink because it's reached its plateau. Now the rate of blinking, or if you get any blinking at all, is really going to depend on the ambient circumstances of the lab. In this case, what is the ambient temperature, what are the air currents that are going over that light bulb, how much insulation is there around the light bulb, and how tightly is it coupled to that temperature sensor. All of these things are going to affect what that final blinking or maybe duty cycle is going to be on that light bulb. So you may or may not get the same exact result, but it should stabilize at your set point. Notice also up here there's a small LED that mimics what is going on with the light bulb. That LED up there on the board is actually connected to the PWM output as well. That's kind of a nice little diagnostic tool. If you get that to blink and your light bulb's not doing the same thing, obviously there's going to be an error in the wiring somewhere. Alright, so since we're meanies, we're going to use this freeze spray, and we're going to lower the temperature of the light bulb. And so you notice that the light bulb has gotten pretty cold, and the temperature's dropped tremendously, and the control system's trying to get it back up to 32. And so you should see that as well. And so now it's getting back up into the 30s. Now I also mentioned that this little dip switch should flip us back between open and closed loop control. So let's go to open loop. Okay, so now we're in open loop, which means that the light bulb's intensity is no longer being controlled by the control system. It's going to be controlled by this potentiometer. As I move this potentiometer back and forth, notice that the intensity of the light changes. And that's full duty cycles. That's 100% duty cycle, and as we get lower and lower, we're getting down to, of course, a low duty cycle back to 0. And so you can see how that affects the temperature. If we have it very hot, the temperature should go high as well. Okay, and since we're in open loop control, you can see the temperature is way above the set point. So let's go back into closed loop control. So I'm going to flip this back down, and so notice that the light bulb turns off because we're way above the set point. We're at 38, and it's beginning to drop back down. And so you should see the same kind of thing when you test your control system out as well. So I hope this explains this lab. Make sure that you get the closed and open loop segment to work, and use the code that you did previously for the temperature sensing A to D conversion.